Okay, so in this lecture, we're going to delve a little bit deeper into the force due to a spring, and we're going to talk about the dynamics and the motion that's associated with springs and masses. And so we're going to start into the process of enriching our mathematics a little bit with some more calculus. And so by the end, we're going to be able to show that there are a set of equations that can describe the motion of the spring quite easily if we just think of momentum changes as being things like derivatives. Okay, so let's start from our normal starting position, and that is that the momentum principle guides our discussion, and it's very useful for both dynamic and static conditions. Right, so systems that are both moving and sitting still, we can start from the momentum principle, but movement implies that we can think in terms of derivatives. So let's rewrite the momentum principle, which is a force equation. So you need to have forces, you need to have momentum, you need to have vectors, you need to make sure that you keep track of all the details. And so this will be F net, as we know. And delta P, of course, over delta T equals F net. That's right. And if we take our limit as delta T goes to 0, these deltas become differentials, and so on the next line we get dp dt equals F net. A very straightforward thing to do. And if we remember, of course, that dp dt is a vector, so that's got to be equal to dp in the x dt, dp sub y dt, and dp sub z dt. Okay? And if we equate this now, we have that this is equal to, of course, F net sub x, F net sub y, and F net sub z. Reminding us that we actually have three equations, three scalar equations that provide us the information we need for our vector derivative. And it shouldn't be any more daunting than that. You think about the x component equating with the x component, the y component equating with the y component, and the z component equating with the z component. And if we do that, if we know the instantaneous change in momentum, we know the force. And likewise, if we know the net force, we know what the instantaneous change in momentum is going to be. They're equivalent. So let's think about how all of this affects a system of springs. Now, we have to rewrite our our spring force in terms now that provide us x. So what we're really looking for, we want x, the position of our mass, x as a function of time. So we can just set the clock running and now let the system evolve. If I pull my spring, how is my mass going to traverse my x direction as a function of time, given the spring force that we know? Okay, so if we do that, we have to deal with the stretch. So x of t for a spring. We have all the makings. We have everything we need. We know the momentum, we know the position, we know the force, so therefore we can start to work. Okay. So let's make the stretch more about the location of the block relative to its equilibrium position. So what we said was that the length of the spring is going to be equal to the rest length of the spring, that's L0, plus its position x along that axis. And so the stretch is now going to look like, of course, L minus L naught. That's how much it displaces relative to its original position, which is now going to be equal to, well, L naught minus x, that's just, or plus x, I'm sorry. That's just this, minus L naught, which is very straightforward. So then S is equal to the position of my spring as a function of time, perhaps, if I want to put it in there. So now, my spring force is equal to minus K of the spring times its x position. Now, this isn't just a single number. This can be any number relative to its equilibrium. And so if we think about this, how are we going to justify this type of definition? Well, let's go in and actually look at the value of the force as a function of these three positions we have here. So let's start with the easy one. X is at its equilibrium position, that is at rest. The spring is not stretched or compressed, so the spring force is of course 0. So we'll say F sub S equals 0. How about here? I've made x greater than 0, so this is a large number, positive number, and so as a consequence, the force is minus that direction, so it wants to draw the spring this way. So here's my force of the spring. Now, let's take x negative. It goes below 0. Here's my 0. It goes below 0, negative number. This becomes positive, so the force is positive. It's actually pushing in this direction. And we can see we've worked out all those details.